As you know, the exam closed on Friday night. There are still a handful of folks that for various accommodations or illness reasons haven't taken the exam yet. Some of them won't be done until tomorrow. So I'm not going to release the exam one review video until the testing center closes tomorrow, because I don't want to give out the answers before some people take the test. So you can expect a detailed exam one review video dropping sometime Tuesday night or Wednesday morning. In the meantime, the TAs, I haven't sent them the key yet. So if you go to them right after this class, they won't have it, but I will send it to them within an hour after the class. So you can go to the TAs and ask questions. You're also welcome to come to my office hours today from noon to 2 or Wednesday from noon to 2 if you want to talk about specific problems on the exam. Let's see. If that doesn't work for you, if there are times that if you can't come during my regular office hours, I can probably make some other time this week, but you'd need to email me and give me a range of times. Probably think about a 15-minute increment or something. Now, overall, the median score on the exam was an 80%. That's historically about how people do on the first exam in 352. That's pretty standard for what I've seen in previous semesters. The average score was around a 76. Median is the 50th percentile. You guys know that, right? Divides the class. Okay. Generally, when the median score is in the mid to low 80s, you can interpret your score above the median with the standard cutoff. So if you're like, oh, I got an 87 on the exam, that's probably a solid B+. Of course, I don't assign letter grades on exams, but what you want to know is, how am I doing? And if you're finishing around 87, you're like, okay, if I continue to perform at about this level, I'm going to end up with a B+. Now, below the median, you can't interpret your score quite as literally with respect to the cutoffs that are in the syllabus. For example, if you finished somewhere in the high 60s, you don't need to be thinking, oh, I failed the exam. You should be thinking, I'm in the range of a C and probably on the lower end of that, possibly C-, but it's certainly not failing, okay? Generally in the class, if you want to get an E, if that's your goal, which I know it isn't for any of you, but you want to earn less than 40% of the points if your goal is to get an E. So if you were finishing in the low 70s, mid to high 60s, be thinking sort of in the C- range. If you want to do better, which I think is most of you, I'm happy to talk to you and provide suggestions. But before you come, I need you to do some honest self-reflection, okay? And this is the painful part. This is where you think, okay, what am I actually doing versus what do I say I'm doing? Generally, when people come, the first thing I ask is, how do you study? And everyone says, well, I do the study guides and the practice exams. And I think to myself, okay, but I think that means something different to you than it means to me, because I can often draw a straight line to how people are approaching the study guides and problem sets to how they do on the exam. So I want you to reflect carefully, how am I actually studying? Are you studying in damage control? At the last minute, you're like, oh shoot, the problem set's due. I got to upload something, so I'm going to look at the key and sort of write something down, and then we're good to go. Or are you actually trying the problems? If you're actually trying the problems, are you getting stuff wrong and investigating why you got it wrong and then practicing? Generally, better performance in the class comes down to better training and better practice. So I'm going to want to talk in detail about what you're doing to study. And the problem is I'm not there, so if you can't provide me any details, then I can't provide any useful suggestions. And don't try to impress me with, oh, how you study. Just tell me how it actually is so we can deal with reality, okay? All right, generally, if you change your approach to the class, you will do better. Generally, I also ask students, how long are you spending studying for the class? And what I mean by that is during a regular week, not the week leading up to the exam. Because I know everybody's like, oh, I can blow it off this week, but we got an exam, now I'm really going to lock in. It turns out that 40 hours in the 24 hours immediately preceding the exam are not as effective as times. Nobody got that? You can't fit 40? Okay, well, whatever. They're not as effective as time spread out over a lot of days. Generally, the sweet spot that people tell me is around 12-ish hours a week. That means most days you want to be spending a couple hours on OChem. And it takes that kind of consistency. Okay, well, I'll have some more personalized suggestions for how to succeed, how to stay up to date, but that's what I would tell you if you came to my office now. As I said, when you come to talk to me, please already have done some self-reflection and examine what you're doing. Because generally the situation is not, I'm doing everything you said I should be doing and I'm still not doing well. Generally there's a problem, and if we can find it, then you can improve. Okay. Well, that was fun. We're 7 minutes in and I was still talking about that. And what the heck, let's make it 10. You guys want to hear a story? Sure. Okay. I had to speak in church not this week because it was Fast Sunday, of course, but a couple weeks ago. Gave me a topic of charity, true sign of discipleship, which is, of course, an indication of something that I need to work on. And anyway, as I was preparing, I started thinking a lot about my grandma who died in October of 2024. And I'm not going to deliver her eulogy here, but before she died, she told my dad, she died within a week of her husband's funeral. They were 94. And she told my dad, I don't want, 95? Yeah, 95. Anyway, she told my dad, I don't want a funeral because they just had the funeral for her husband a week previously. She's like, just do a graveside service. And I was kind of angry because I felt like there were songs that should have been sung and things that should have been said. So I felt like when I was giving my talk, I felt like talking about Grandma as just the way she loved and laughed as an inspiration and sort of an example of what charity or the pure love of Christ is. Anyway, the Saturday before I spoke, I was thinking about her, and her favorite song, which I wished would have been sung at her funeral, was How Great Thou Art. And so I'm just driving around running errands on Saturday, Costco Saturday. Those hot dogs are not going to eat themselves. And I just prayed and said, Lord, this isn't really a big deal. If you don't want to do it, it's not that. So don't put yourself out or anything. But if we could maybe sing How Great Thou Art tomorrow in sacrament meeting, that would be awesome. So I'm sitting there before sacrament meeting playing the prelude on the organ because that's my job. And I'm watching the chorister put the numbers up. And I had already, figuring I would fulfill my own request, I already played How Great Thou Art as part of the prelude. But then I see the chorister, and she doesn't know that I was hoping this would happen. And, she's putting up the numbers. Okay, that's not it. And then the last number's 8 and 6. And that was, which is actually, if you don't know, the hymn number for How Great Thou Art. So that was sort of a little love letter from heaven. There's a lot of problems I've asked God about to make better, and I've gotten the answer I get is just keep moving forward, it'll be fine. And I'm like, yes, but you could fix this. And he's like, it's fine, just keep moving forward. But occasionally, in things that are small, you can ask and God will give you an answer, and it's a little bit of a love note from heaven. And that's the way it was for me that day. So anyway, I hope you know God's aware of you as well. And at this point in your life, he wants you to listen and learn organic chemistry. So, shall we?
Why is your setup green?
Why is the setup green? Ooh, that's ugly, isn't it? My guess is that's a kink in the HDMI cord. Let's see if it gets better. Much better. I should have just gaslit you. I just should have said, it's not green to me. Yeah. It would have worked, yeah. You trust me, right? Okay, so we were talking, we need to finish up on nucleophilic acyl substitution, just biological examples. I showed you 2 ways that you can convert a carboxylate biologically from being a not electrophile to a group 1 reactivity electrophile. This is using ATP. Now, I said ATP is generally reactive at either the gamma phosphorus or the alpha phosphorus. Some of you came up and asked, how is that, and why is one more reactive than the other? And the answer is, it's context dependent, it's enzyme dependent. Some enzymes will hydrogen bond with the phosphoryl oxygen on the gamma, and that activates it towards attack. Others will do so on the alpha phosphorus. You're not meant to predict which is which, but you'll be able to tell based on the enzyme name in a lot of cases what the enzyme does. If the enzyme name is kinase, probably it's transferring the gamma phosphorus group. If it's something else, we'll worry about that later, and you'll learn in biochemistry. So I showed you how the carboxylate, if it attacks the gamma phosphoryl group, you get this pentavalent intermediate. That's analogous to a tetrahedral intermediate, not exactly the same thing, but basically phosphoryl groups do carbonyl chemistry. Electrons kick down, and ADP leaves as a leaving group, and you end up with this acyl phosphate. You'll see a reaction like that in this semester when we talk about glycolysis. And this is a good leaving group. This is now a group 1 electrophile. Alternatively, if we attack the alpha phosphorus, we get, and then what gets kicked off is this leaving group. This leaving group is called pyrophosphate. It's a great leaving group. And the other thing about it's often abbreviated in biochemistry textbooks as 2 capital letter P's with a subscripted I. The subscripted I just stands for phosphate that's inorganic, meaning it's not attached to anything that's carbon. Pyrophosphate is a great leaving group and actually can be hydrolyzed to 2 phosphate ions via a very thermodynamically favorable reaction. But over here, you've got the carboxylate nucleophile now attached to the alpha phosphoryl group, and that alpha phosphoryl group is attached to the ribose ring. This is called an acyl-AMP, where AMP stands for adenosine monophosphate. This is also a group 1 electrophile. Acyl phosphates and acyl-AMPs react analogously. They both are group 1 electrophiles. They both can do nucleophilic acyl substitution reactions. You can see, though, that they are structurally different. This one just has the phosphate, which is negatively charged. This one has a whole other thing over here. And that whole other thing over here can be important for the enzyme to grab onto. Enzymes can specifically recognize acyl-AMPs. So you'll find in biochem that their uses are a little bit different. We're not going to learn about that in a lot of detail for now. I just want you to have the idea of these 2 different possible kinds of biological electrophiles. Here's an example of what nature can use an acyl-AMP for. So I'm just going to copy this, and let's assume that our carboxylic acid was not, in fact, just an R group. Let's suppose 2, 4, 6, 8, 10, 12, 14, 16. All right, this is a C16 fatty acid, and now it's actually the fatty acyl-AMP. So the precursor would have been the 16 carbon carboxylate. Sorry, oops, erase. And nature would, with ATP, react this fatty acid to make the fatty acyl-AMP. Where do you get the C16 fatty acid? That comes from ester hydrolysis. Now, we learned last time about ester hydrolysis. We called it acid-catalyzed ester hydrolysis or saponification. Nature has an enzyme to do that, to hydrolyze the ester in a triglyceride. It's called a lipase. And so the fatty acyl-AMP is released by the lipase. Then your body activates it as the acyl-AMP. And then your body does a nucleophilic acyl substitution reaction. And the nucleophile is called coenzyme A thiolate, which will draw like this. So I will draw the structure of coenzyme A for you. You will wish I had not once I draw it for you. For right now, you can think of it as just a negatively charged sulfur. As you would expect, electrons kick up. We get a tetrahedral, the sulfur attacks the carbonyl carbon. We get a tetrahedral intermediate. I'm going to abbreviate everything in this mechanism so we don't have to redraw a bunch of stuff. The R group here is the fatty acid chain. OAMP stands for the green stuff, which was the leaving group. SR is the nucleophile. And then electrons kick down, kick off the OAMP good leaving group, and you're left with this, which I guess we ought to put primes on everything. And this is now a thioester. So nature can take the group 1 electrophile, that's the acyl-AMP, and it can swap out nucleophiles to make another group 1 electrophile, the thioester. So why would nature bother to do it? Can't we use the acyl-AMP for things? Well, as I told you, the identity of the leaving group can provide a handle for the enzyme to hook onto and to hold onto, and sometimes changing that handle allows the molecule to be a substrate for different enzymes. I'm going to show you, as long as you can remember that the R on the acyl group is all of this, I'll just show you briefly the structure of the thiol. So here is the sulfur. There's a 2-carbon chain and a nitrogen. Then there's an amide. Then there's another amide. I'm not making this up. This is actually what nature does. So if you're like, why does it have to be that way? One answer is, I don't know, but it's nature, so I'm just telling you what is. All right, there's more. You tired yet? I'm tired. Let's see, there's an OH group here. This one happens to be a phosphoester, which is all kinds of fun. And then there is the adenine base, which I'm going to abbreviate with A. So all of this was that SR group, and we call all of it basically coenzyme A. It's a cofactor, or CoA for short. It's a cofactor in a lot of reactions, and again, this provides a handle for some enzymes to hold on to. So we will normally just draw this thiol as an S with a CoA by it to remind us what this is. That coenzyme A thioester with the fatty acid group is now a substrate for enzymes that can break the fatty acid up into smaller chunks. So burning fat, fatty acid metabolism involves these steps like I've shown you. Okay? What's there to memorize there? Do you want us to memorize the structure of coenzyme A? No, I had to look it up. I don't have it memorized. But you should recognize that the thioester is a group 1 electrophile and itself can do nucleophilic acyl substitution chemistry. I want to show you one more thing from biology, and then we've really spent too much time on chapter 16, so we got to move on. This is a figure from your text. Here is a thioester of a fatty acid. I just showed you how to make that, okay? Start with the carboxylate, make the fatty acyl-AMP, and then do a nucleophilic acyl substitution with coenzyme A. That gets you here. If you're not going to metabolize the fatty acid, another thing that you can do with it is to make an ester with the OH group of cholesterol. So there's an enzyme that catalyzes this reaction, but essentially this is the carbonyl carbon, that's the carbonyl oxygen, coenzyme A is the leaving group, and this OH group is the nucleophile. So you can see after this reaction, the leaving group has left, the nucleophile is now attached to the carbonyl carbon. And there is a tetrahedral intermediate which isn't shown. This has the effect of turning the cholesterol, which had a polar group on it, into a cholesterol ester, which is now just nonpolar all the way around. Cholesterol is pretty nonpolar, so to be transported in your blood, it has to be encased in this lipoprotein particle. This is a particle that has membranes in it and has phospholipids and proteins and then cholesterol. The yellow spheres here are ordinary cholesterol molecules that are packed in this phospholipid particle. The polar portion, which is the OH group, is exposed to solvent. The yellow blob here, and there's some others here, is a protein component of this particle. And then encased inside, it's like a micelle. This lipoprotein particle is like a micelle, and packed inside are these orange spheres, which are cholesterol esters. There's this whole nonpolar thing. And these are the HDL and LDL particles that are in your blood that when you get a lipid panel, they're analyzing these. LDL delivers cholesterol esters to tissues. HDL picks up cholesterol, transports it to the liver where it can be metabolized and degraded. This is why we call HDL the good cholesterol and LDL the bad cholesterol. This is not a physiology class, so we're not going to learn about atherosclerosis, but the plaque that's associated with like clogged arteries and ultimately heart attack has a major component of cholesterol esters. They start to get deposited. How that happens is a complicated process, and we're not going to talk about it in any detail, but the stuff that's getting deposited there is this molecule. Okay, so that's enough on chapter 16. We need to now turn our attention to checkpoint 17.1. And the theme of chapter 17 is we're going to use a new kind of nucleophile. And the new kind of nucleophile is going to be called either an enol or an enolate. And it's related to carbonyl chemistry with the idea that protons that are alpha to carbonyl carbons are acidic. We've talked about that recently. I talked about sigma to pi star hyperconjugation. Here is the carbonyl group. We got the carbonyl carbon, you've got the carbonyl oxygen. And you're used to thinking of the LUMO of this molecule as being the carbon-oxygen pi star, and it is, but, or and, there is something else going on. Due to sigma to pi star hyperconjugation involving the adjacent CH bond on the alpha carbon, some of the LUMO is actually on the alpha proton. I showed you that before. We can also go to Spartan and look at our carbonyl molecule and download what the LUMO should be. And you can see that the LUMO, we'll turn it off again, and you can see where the carbonyl is and where the alpha protons are. The LUMO is mostly the carbon-oxygen pi star, you can see a lobe on the carbon, a lobe on the oxygen. Most of it's on the carbon. So a nucleophile would attack at the carbonyl carbon. But you can also see there's a little bit of LUMO on the adjacent alpha protons. That's because of sigma to pi star hyperconjugation, which means that a nucleophile can choose to attack at the carbonyl carbon, that's being a nucleophile, or it could choose to attack at the alpha proton. That would be called being a base. So we've dealt with extensively in our first unit, chapters 13 through 15 and then 16, with attack at the carbonyl carbon. In chapter 17, we're going to be dealing with attack at the alpha proton and what that does. Okay? So, supposing that you have a base of some kind, a base slash nucleophile, you can remove the alpha proton, and that will get you to the following intermediate with a negative charge on the alpha carbon. And that you should recognize is resonance stabilized because the negatively charged alpha carbon is conjugated with the carbon-oxygen pi bond. So you should be able to see how I can, with just arrow pushing of these electrons, move the lone pair over to form a pi bond between alpha and carbonyl carbon, and then move the carbon-oxygen pi bond out onto the oxygen. This is called an enolate. Okay? Enolates are resonance stabilized. Because of that, the CH proton, the alpha proton here, which I'm going to highlight in orange, is actually more acidic than a typical sp3 hybridized carbon-hydrogen bond. If you go look up on a pKa table, the typical pKa for an sp3 hybridized carbon-hydrogen bond is like in the 40s or 50s. In contrast, being alpha to a ketone makes your pKa much lower, closer to 20. And why then would the pKa of the alpha proton be 20 when the pKa of a typical CH3 bond, or a typical sp3 hybridized carbon-hydrogen bond, is 50? The answer is because the conjugate base is resonance stabilized. Okay, questions about that? Now, one thing you need to know about enolates is enolates are nucleophiles. The enolate itself is really a conjugated pi system. If you want to pick the HOMO of the enolate nucleophile, you would have to conclude that the HOMO is either the lone pair on the alpha carbon or the lone pair on the oxygen, but it's actually delocalized. Okay? Now I'm going to remind you without explaining it in a lot of detail, and for more information you should go to chapter 12 in 351 about conjugation, resonance, and so on. The MOs of the highest energy MOs of the enolate would include a pi1 orbital representative of the electrons in the pi bond that are delocalized between alpha carbon and carbonyl carbon in this resonance structure, and between carbonyl, oxygen, and carbon in the other resonance structure. But the HOMO would actually be the lone pair, and MO theory tells you that that lone pair in a pi2 orbital is delocalized on carbons 1 and 3, but never on carbon 2 with a node in between them. Of course, there's also a pi3 empty orbital that we're not going to worry about or draw because it's not relevant to our discussion today. But what you need to know is that the HOMO of the enolate nucleophile is both on the carbonyl oxygen and the alpha carbon. But for the most part, and I can't say always because there are counterexamples in organic chemistry, but none that you will encounter, the enolate nucleophile is going to be primarily reactive at the alpha carbon. Okay? Now, what we've just done is talk about deprotonating a carbonyl compound on the alpha carbon to get an enolate. Of course, whatever base we used, we would now have, if the base was negatively charged, we would now have this conjugate acid. If the enolate gets protonated again on the alpha carbon, that would simply involve these electrons attacking the hydrogen and then breaking the bond between the hydrogen and the base. We would go back to starting materials. That's what's meant by this reverse arrow. So, but if the enolate gets protonated on the oxygen, then you get this other isomer called the enol. And that process of going from ketone starting material to enol is called tautomerization. Except I can't spell tautomerization. You've seen that before. Tautomerization simply involves removal of a proton to give a resonance stabilized intermediate, and then protonation of that resonance stabilized intermediate on another atom. Okay? Now, in this equilibrium process, we'll call the starting material the keto form, and then we'll call the product the enol form. The keto form is more stable because carbon-oxygen pi bonds are more stable than carbon-carbon pi bonds. So generally, we will expect ketones to exist mostly in their, we will expect carbonyls to exist mostly in their keto forms, though depending on the context, there may be some amount of enol present at equilibrium. Okay, questions about that? All right, now we need to talk about the different kinds of alpha protons, and we need to get a sense for alpha proton acidity and the role of this base in how much enolate you form. Go ahead.
Is there anything you can do to the solution to prefer the enol versus the ketone?
Can you do anything to the solution to prefer the enol versus the ketone? There are things you can do to the structure of the molecule to prefer the enol versus the ketone. There's like one example of that, and it's kind of cute. It might actually be in your problems at the end of the chapter, but we're not going to spend any time on it here. By altering the base, you can cause the enolate to be the major product, but I'll illustrate that in a second. All right, so let's talk about alpha proton acidity. And we're going to look at some different kinds of carbonyl compounds. And I want you to notice a trend, okay? So, and it's going to, as I draw a carbonyl compound, I want you to be thinking, okay, is that a group 1 electrophile, a group 2 electrophile, a group 3 electrophile, or so on? All right, so here is an amide. Let's just put 2 R groups on that amide, and we're always talking about the acidity of the alpha proton. Okay, the pKa, and then we'll draw pKa for the amide is 30. That's for the alpha proton of the amide. Instead, if we do an ester, the pKa lowers to 25. If we do a ketone, the pKa lowers to 20. And if we do an aldehyde, the pKa lowers to 17. So tell me about that. What trend does that follow? What kind of electrophile is an amide? That's group 3. It's group 3 because the thing attached to the carbonyl carbon is not a great leaving group. It's also group 3 because the thing attached to the carbonyl carbon is a nitrogen with a lone pair on it, and that's a good electron donor. Do you remember we talked about that? The carbonyl carbons can be stabilized by resonance with the adjacent heteroatom, and the better that heteroatom is at donating electrons, the less electronegative it is, the more that donation will occur, making the carbonyl carbon less electrophilic. Okay? Notice that esters are group 2, more reactive electrophiles. So it appears that the trend is the more reactive the electrophile is at the carbonyl carbon, the more acidic the alpha-proton is. Okay? If you go to the aldehyde, which is the ketone, which is group 1, you're again 5 pKa units more acidic, and that's because the ketone lacks any kind of electron donor. The ketone has a CH3 group on the other side, which can donate electron density into the carbonyl carbon, but not as well as an OR group or an NR group. And of course, for the aldehyde is even more electrophilic than the ketone because CH3 groups are decent donors of electron density via an inductive effect. Hydrogens are not. So you will see that the group 1 electrophiles are much more acidic on the alpha carbon. The rationale for that is just to think about, and I'm not going to draw all of these, and I'm going to trust that you can reason through this, to think about the conjugate base, and I'm going to draw the conjugate base of the aldehyde, and then I'm going to draw the resonance structure where we have a pi bond between the alpha carbon and the carbonyl carbon. You can see that one of the things that stabilizes the conjugate base is the ability of these lone pair electrons on the alpha carbon to become a pi bond between alpha and carbonyl. The idea is that resonance structure is less of a thing, less of a major contributor if you already have a donating group over here pushing into the carbonyl oxygen. Okay? So the moral of the story is you can use everything you've used so far to rank electrophilicity of carbonyl compounds to also rank acidity of alpha protons, where the most electrophilic carbonyl compounds will have more acidic alpha protons. Okay, do we need to say any more about that, or you got the trend? Okay, one item we need to put on the list here. It's about the same pKa as the ester. It's something that is difficult to remember because when you see the nitrile, you don't necessarily say to yourself, oh, look, that looks like a carbonyl. But effectively, it's the same thing. Protons that are alpha to nitriles. Nitriles are electrophilic in the same way that carbonyls are electrophilic. So protons that are alpha to nitriles can also be removed to generate enolates. And those enolates are resonance stabilized. So you can think of nitriles as being basically like carbonyl compounds. And this will come up a little bit in some of the practice problems. Okay. We're not yet done with alpha proton acidity because you can change the structure a little bit and you can make alpha protons that are even more acidic. So what if instead of having a proton that was alpha to just one ester, what if we made it alpha to 2 esters? This is called, by the way, a beta diester because you've got a second ester beta to the first. Turns out that pKa is like 13. Now, I'm trusting you to figure this out, to read it in the text. We don't have time for it today. But if you drew the conjugate base of this beta diester, I'll just draw you one of the resonance structures. You should easily be able to draw me two other resonance structures in which the negative charge is on a carbonyl oxygen. Do you see that that one has two places it can go? That's why this is so much more acidic. It's acidic by a factor of 10 to the 12, so 1 trillion times more acidic to have a second carbonyl. And you will see that beta dicarbonyl compounds are more acidic. Now, let's mix and match. Supposing I take this same compound, but instead of having an ester on both sides, I have an ester on one side and a ketone on the other. You predict more or less acidic than the beta diester? More. Why? Because ketones are more electrophilic than esters, and alpha-proton acidity is going to track with electrophilicity. So, if we have a ketone here and an ester here, you're exactly right. The pKa for that is 11. And again, that tracks with what you expect. This is called a beta keto ester. And there will be questions in your text that'll just show you dicarbonyl compounds and ask you to rank them in acidity without showing you the pKa. What do you predict for this one? Two ketones, more or less acidic than the beta keto ester? More, because ketones are more electrophilic than esters, and that pKa is around 9. Okay, so we've got a huge range of alpha-proton acidity. Importantly, notice that some of these, the beta diesters, the beta dicarbonyl compounds, are acidic enough to be deprotonated by OH minus and alkoxide bases. Like, for example, ETO minus. This is gonna, and if what I just said didn't make sense, then you're gonna need to remember and pick up a skill from chapter 2 of 351, where we asked, is this base strong enough to completely deprotonate things, right? Do you remember how to do that? How can you tell if a base is strong enough to remove a proton? Yes? Its conjugate acid of the base must have a higher pKa than the pKa of the proton in question, right? Good. So the conjugate acid of the alkoxide bases or OH minus is water or alcohols, and that pKa is 16. So ETO minus or OH minus can completely deprotonate these. Now, what about these? Let's look at the equilibrium, and let's do this with an aldehyde. So suppose we had ETO minus, oops. And suppose we had an aldehyde, and the pKa of the proton that's alpha to the aldehyde is 17. Let's ask ourselves, where does equilibrium lie towards our starting materials, which has the alkoxide, or towards our products, which have the enolate? To decide this, you write the pKa of whatever acid you've got, and the strongest acid loses its proton. So equilibrium favors what? Starting materials, right? But by how much? So each difference, each pKa unit of difference between the acids on one side tells you pK is a log scale. So if it's 1, this tells you that it's 10 to 1 products starting materials to products. Or in other words, and the numbers aren't going to be exactly right, we're not going to get this because I can't do the math in our head, but we'll just say about 10% and 90%, okay? Now back in 351, when you were answering, can this base remove this proton, the standard was 100%, right? Or at least greater than 50. For now, it turns out even though 10% is small, it's still useful. And we can do things with that 10% of enolate. We will call a strategy where we don't make 100% enolate formation, we will call this reversible or equilibrium or thermodynamic. We'll use those terms interchangeably, enolate formation. That phrase, thermodynamic enolate formation, is going to be important to you. And if you go ahead.
Sorry, just when you drew the what's supposed to be an aldehyde, it's actually a ketone.
Yes, thank you. Sorry, I'm missing an H, aren't I? There we go. Good. Okay, so what if I wanted 100% enolate formation? I just need to use a base whose conjugate acid has a pKa greater than 17. So let me introduce a base that is really good and is basic enough to remove most alpha protons of most carbonyl compounds at the level of about 100%. I'm going to call this quantitative enolate formation. 100% not reversible. Okay, so here is the base. It is called lithium diisopropyl amide, where amide is also a term that's used for a negatively charged nitrogen. Lithium is just the counter ion. This is called LDA for short. That's how your text will refer to it. We're going to use the aldehyde again. The proton that's alpha to the carbonyl carbon has a pKa of 17. If we want to ask which direction does equilibrium lie, we have to draw the conjugate acid of our base, and then we can draw the enolate. You can draw whatever resonance structure of the enolate that you want. The pKa of that conjugate acid is of our LDA base is 40. So we brought the big guns. That's 100% complete and utter deprotonation. So we would get 100% enolate and 0% starting materials. So this is not reversible enolate formation. Which base you choose can affect whether you form a little bit of enolate or a lot of enolate. Now, you're saying, why would you ever want to form a little bit of enolate? Why not just go with 100% enolate all the time, and then you can go on to use that enolate as a nucleophile? The answer is two things. First, LDA is more expensive than say, an alkoxide base, because LDA is more reactive. So that's one reason. The second reason is you will see that we actually get different enolates when we use alkoxides versus LDA on non-symmetrical ketones. So, behold a ketone. You're going to see that if we use LDA versus an alkoxide base, we're going to get different enolates. You should be able to see, based on what I've drawn for you here, we have two different kinds of alpha carbons, two different kinds of alpha protons. And what a great cliffhanger. When we get back next time, we will talk about that. So we are not quite through with checkpoint 17.1, but we're close enough. We'll move on to 17.2 next time. I will see you Wednesday.